Welcome back to Bio 6612. We're going to look at some more Poisson regression examples in R in this lecture. I have an additional book that I've added to the optional readings list here, which is a book on applied multiple different types of regression in R. And the chapter 4 talks about Poisson regression and is a nice resource, so I highly recommend it. So first we're going to go back to the fertility data example from the first lecture in Poisson regression. And this data comes from a 1985 study of German women aged 44 or older and in first marriages at the time of this study. And we're interested in the outcome number of children per woman based on a large set of explanatory variables. So the outcome is number of children per woman. And here the unit of observation is woman. So data is at the individual level rather than the cell level. I've mentioned a couple of times now that with Poisson regression, the counts can be at the individual level or the cell level. If you are at the individual level, then you have counts per person, like is the case here. If you have data at the cell level, then you have counts per cell in a table. So you can load this data into R by loading the library counter and data fertility. And then this statement here runs that model where children is the outcome, and you have 1, 2, 3, 4, 5, 6, 7, 8 covariates that we're running in this model. And so I've output a table here which includes the exponentiated estimates and a confidence interval and p-value. And the way that I extracted these elements is using the tidy function from the Broom package. And this function is really nice because it can take objects from GLM or LM, and you just feed in the name of the object, and then it extracts things for you, like the estimates, and puts them into a data frame so they're easier to work with. And in this case, I've added a couple arguments to that function, one being exp equals true, which returns exponentiated versions of the estimates. So in this case, it exponentiates our betas so that we have rate ratios. And this confident equals true means that you're going to get confidence intervals as well. And since x equals true was given, then the confidence intervals are going to be exponentiated as well. And so then I'm just selecting the terms I'm interested in, I'm formatting the p-value, and then I'm using the table function from the knitter package to produce a nicely formatted table for the output. And so here the exponentiated coefficients, the rate ratios are given in this column. And you can see several significant p-values. And so on the next page, I interpret some of the findings from this model. And these are not formal interpretations, they're just some takeaways from this analysis. And these are controlling for other covariates in the model. We can say that German women have significantly lower rate of birth than non-German women. Women with vocational training have a significantly lower rate of birth than women without. Both Muslim women and women from other religious categories have significantly higher rates of birth than Catholic women. And women with higher age at marriage have significantly lower rates of birth than women who were younger when married. So now I'm going to go through another example. These are the Danish lung cancer cases. And this is an example that uses an offset term. So offset terms are necessary when for each cell you have a different denominator for the time of exposure or number of things exposed. So you'll see what I mean in just a minute. But in this example, we're interested in the association between age and city of residence and the incidence of lung cancer, where incidence of lung cancer is the outcome. So this data is reported in aggregated form or in counts per, which means counts per cell rather than counts per individual. And we need an offset to account for the different number of people at risk in different cities or age groups. This data comes from the ISWR package and is called EBA 1977 is the name of the data set. So this is how you will load that data into R. And just briefly looking at it, if you imagine this is a table, so this is in tabular format, then each of these rows would be a cell. And you have the covariate city and age, which is grouped as a categorical variable rather than a continuous variable here. Then you also have cases, which is your outcome. That's the number of lung cancer cases. And then you have this pop variable, which is the total population in each of these cities. So when we say we need an offset term to account for different numbers of people at risk in different cities and age groups, what that means is that in the 40 to 54 age group in the city Fredericia, I think that's how you pronounce that, the population is 3,059, and there are 11 cases. Whereas in the city Horsens, in the 40 to 54-year-old age group, there are 13 cases and only 2,879 people. So here we wouldn't say that 11 and 13 cases are directly comparable because there are different numbers of people in each of these cities and age groups. So we need to account for the fact that the population is going to be different in each of these cells when we're doing this analysis of the number of cases. So the first model I'm going to look at is an intercept only model because we can estimate the rate of lung cancer per capita or per person across all cities and age groups with an intercept only model. However, we're still going to need an offset term to account for the different number of people at risk in different cities or age groups. And so here's our model. Cases is the outcome. I'm running that against 1 because I want it to be an intercept only model. I'm not adding other covariates. And then I also have this offset log population term. So where exactly is this offset term coming from? Well, we talked about this a little bit in the previous lecture, but the Poisson model says that the log of the expected value of yi given xi over ti, where ti is the term that accounts for different time or person time at risk for the number of counts, which in this case is our population for each city, is equal to xi transpose beta. And in the last lecture, we showed that we can rearrange that and get log of expected value of yi given xi minus log of ti equals xi transpose beta. And then bringing this log ti term to the other side, what you end up with is log expected value of yi given xi equals xi transpose beta plus log of ti. Okay, so we have our outcome. That's our outcome. We have our link function g. We have our covariate terms, and we have our offset. So the way that you set that up in the GLM model, in the GLM function in R is, okay, so we have our outcome, that's our counts here. We set that up with y against, in this case, we use 1 because we don't want any, we just want an intercept. We're not adding any covariates. And then the offset is log of the population. And from this way that the model is set up, That's why you know you have to take a log of the population when you put that in the offset term, rather than just putting the population there. You need the log because that is coming from this particular model. And then the other thing that I want to point out, the reason that you can't just throw in log of population as a covariate is that's going to estimate some kind of beta in front of that log term. But you actually just want the beta to be equal to be restricted to only be equal to 1. What we're going to end up with overall is lambda I, which is going to be the expected rate of lung cancer per person. So the value that we end up with for beta 0 is given here, beta 0. In this case, the intercept is the log rate of lung cancer per person or per capita in the Danish population at the time the study was conducted. So if you exponentiate that beta 0, and what you don't see from this code here is this value is e to the beta 0, not beta 0, sorry about that. Then the expected rate of lung cancer for each person also, or the risk of lung cancer, is 0.008. So saying the rate of lung cancer for one person, instead of saying that, we might want to report the rate in terms of cases per 1,000 people. And you can get that by multiplying the exponentiated coefficient by 1,000. And similarly, you can do that to the confidence interval to get the confidence interval per 1,000 people. And this gives the expected rate of lung cancer per 1,000 people in the Danish population. So the expected rate of lung cancer per 1,000 people is 8.48. So let's say we would like to look at the association between city of residence and lung cancer incidence adjusted for age. So I'm going to run a second model here. I still have to include the offset term for the population per city and age group, but I'm now also adding the covariates city and age that we're interested in. I'm going to again use the tidy function from the Broom package and exponentiate the coefficients to pull out exponentiated coefficients from this model. And these are printed on the next page. So one of the things about this data is that the city of Frederica has a substantial petrochemical industry, and the researchers believed this may have some kind of effect on the incidence of lung cancer in that city. In this analysis, Frederica is the reference group, and each of the other cities has a lower lung cancer incidence rate adjusted for age. And you can see that here where Horsens compared to Frederica is lower. All of these rate ratios are less than 1, which indicates for each of them they have a lower rate of lung cancer than the reference group, Frederica. And also age has an increasing effect on incidence of lung cancer. Here, the lowest age group, the 40 to 54, I think maybe it's 45 to 54, is the reference category. And each of these rate ratios is greater than 1, indicating that they all have a higher rate of lung cancer incidence than the smallest age group reference category. So let's look at a couple interpretations from this data. And I'm going to look at exponentiated interpretations. So in this example, the intercept is interpretable as the log rate, or you could also say log incidence of lung cancer for a person living in Frederica in the 40 to 54-year-old age group. And that's because this is the reference category here, and this is the reference category. We have exclusively categorical variables in this data set, so the intercept is interpretable. So the way that we would interpret the exponentiated intercept is that the incidence of lung cancer for a person in Frederica is in the 40 to 54 age group is 0.004. For the first, the beta coefficient, which compares Horsens to Frederica, we would say that the rate ratio of lung cancer comparing a person living in Horsens to a person living in Frederica, controlling for age group, and is 0.72. Alternatively, you could say that the rate of lung cancer in Horsens is 0.72 times the rate of lung cancer in Frederica, controlling for age group. Or you could express this as a percentage. The rate of lung cancer is 28% lower in Horsens than Frederica. And where does this come from? You can get this by saying 1 minus the rate ratio, which is 0.72, times 100. That's how you express that as a percent. I'm also interpreting the beta 4, which is one of the age group categories here. And here we'd say that the rate of lung cancer for a person in the 55 to 49, that should be 55 to 59 actually. 55 to 59 age group is 3.0 times the rate of lung cancer in the 40 to 54 age group, controlling for city. So what if you want to look at the overall effect of city? Because there are 4 cities in the data set, we represent the effects of different cities through 3 indicator variables, which can be seen in the output table. Because Frederica is the reference category, we compare the rate of lung cancer in each city to the rate in Frederica. However, how can we test if the rate of lung cancer differs by the city, the location, city, overall? Like what if we want to test all of those 3 betas at once? Well, we can use a likelihood ratio test like we did for logistic regression to do this. And the likelihood ratio test that we would be conducting is for the null hypothesis that each of those betas are equal to 0. Alternatively, you could say that city and lung cancer incidence are not related or are independent. So in order to conduct this test, first I'm going to run the reduced model, which is a model without city as a covariate. So this model is exactly the same, except we're not using city as a covariate. We still have the offset term. And then I can use a ANOVA model to compare the reduced model with the full model. Using a likelihood ratio test. And this produces the following results, where the difference in the degrees of freedom for each of the 2 models is 3, and that's because there are 3 different betas. The test statistic will follow a chi-squared distribution, and it gives you a p-value, which in this case is not significant at the 5% level. So though the rate of lung cancer is highest in Frederica, the overall effect of city on the rate of lung cancer is not significant. So finally, I'm going to go through an example of a contrast Contrasts can be used when you want to test more complicated hypotheses than those that are automatically returned by the output of the model. And in this case, suppose we want to test if the log rate in Frederica is different from the average log rate in the other 3 cities. Basically saying, okay, is there a difference in log rate comparing Frederica to the average of the other cities? And we can use a contrast statement to do that. When we're testing the following null hypothesis. And if you have questions about why, then post on the discussion board, and I'm happy to go through that in more detail in one of the labs. And this test has only 1 degree of freedom because we only have one equality that we're testing here. So to actually implement this in R, you build a contrast vector. That's what's here. You multiply that by the coefficients of your model. And then you calculate and that gives you sort of the mean of the contrasts, and then you can get the covariance matrix of the contrast by multiplying that contrast vector by the covariance matrix of the model, and then again by the contrast vector. And this allows you to get a Wald statistic, which is calculated here. And in this case, we calculated the standard normal version of the Wald statistic, so this will do distributed normal 0, 1. However, instead you could do that quantity, the difference over the standard deviation of the difference squared, and that would have a chi-squared with 1 degree of freedom. Either way, so this has a standard normal variant distribution. That's a pretty large value, so that's probably going to have a small p-value, and you're going to end up rejecting this null hypothesis.